So for FRQ number 1, part A, it asks us to draw a feed body diagram of the cart right here. So the cart, we have a force, I'll call it force tension, that's pulling it to the right, which is derived from this string right here, connected to the force sensor. We have an FG, we have an FN, and then we also have friction that's opposing the motion, so F friction, like that. Okay, and then for part B, it asks us to plot all the data points for the acceleration of the cart as a function of the force reading, sensor reading, and then draw a straight line that best represents the data. So I just labeled all the intervals right here on the x-axis and y-axis, and then my x-axis is my force, and then my y-axis is my acceleration. So right now I'm just gonna plot the points for you. Excuse me. So at force sensor reading of 0.32, we have 0.12, which is going to be somewhere around here. That 0.38, we have 0.22, and 0.44, we have 0.33. Here, 0.5, we have 0.5. That 0.6, we have 0.7, which is around here. There you go. Make these more noticeable. That, and now I'm just gonna take a ruler and draw the line that best fit in. That. Okay, that's it for part B. And then for, okay, never mind. There's other parts to part B. So for part B, first one, use the straight line from the graph, calculate the mass of the cart. So what I know is that all the forces equal mass times acceleration. So to separate for and to isolate for mass, what I did was force over acceleration equals mass, like that. So I know that all the forces on this reading right here divided by the acceleration is going to give you my mass. So what I'm going to do is I'm going to use the points from the line of best fit right here to basically estimate my mass, because these points right here, like when you divide them, they vary. So I'm just going to take points from the line of best fit and then use those to average it out and then divide to calculate for my mass. So I'm going to use some points from my line of best fit. I see that right here I have with certainty 0.6 and then 0.7. And then I'm going to use my x-intercept as well. I see right here is 0. And then this right here looks like 0.27, like that. So first it's going to be forces on top. So it's going to be 0.6 newtons minus 0.27 newtons over the acceleration, which is going to be 0.7 meters per second squared minus 0 meters per second squared, like that. And that's when you plug it into the calculator, it's going to give you 0.471 kilograms. And then that should be around the estimate of what the mass of the cart is. Part 2. As using a straight line from the graph, determine the magnitude of force of friction. So it's asking for force of friction right here. I know the force of friction is the x-intercept. Okay, so I know it's the x-intercept because at the x-intercept, acceleration is 0. So we know that it's force tension minus force friction equals mass. And then when acceleration is 0, that means that the force of tension equals the force of friction. So when the force sensor reading n right here is on the x-axis, that means the acceleration is 0, which means that it is the same value of force that the force of friction is exerting as well, because the force of friction is counteracting the force sensor reading when acceleration is 0 and perfectly counteracting that as well. So I know that when acceleration is 0, that means the force of that means that the force applied by the force sensor reading when you're pulling it is equal to the force of friction that's counteracting that motion as well. So I know that Fs is the x-intercept, and then as we saw right here, the x-intercept we labeled as 0 and then 0.27. So 0.27 is, oh oops, I labeled it wrong. I switched it, my bad, I'm sorry. It should be 0.27 and 0 right here, because acceleration is the y value. So we know that force of friction is 0.27 newtons. Part C asks us to determine the acceleration of the block of the cart, and then it says that the constant force sensor is reading 0.45 newtons, and then it's being pulled for 2 seconds. Okay, so delta force, sigma force equals ma, like that. So we know that force tension minus force friction divided by m is going to give you your A, like that. So force tension, they said that it's exerting 0.45 newtons of constant force, minus force of friction we found was 0.27 newtons, over our estimated mass of 0.471 kilograms. So acceleration should equal out to be 0.381 meters per second squared, like that. Part D asks us to, when the spring breaks at t equals 2 seconds, calculate the time it takes for the cart to stop after the spring breaks. So we know that the spring breaks at t equals 2 seconds. So I'm going to find the value of the velocity at t equals 2 seconds. When I know it's v initial plus at. We know v initial is 0, so it's at. So we use the acceleration that we found previously. We know it's 2 seconds. So we know that the velocity at 2 seconds is 0.764 meters per second, like that. So now, when the string breaks, that the only force acting on the cart is the force of friction. So sigma F equals ma. So we're gonna find out acceleration again. So negative force of friction because it's acting against the motion. Mass equals A. So negative 0.7 newtons, 27 newtons over 0.471 kilograms, like that. And then that's gonna equal negative 0.573 meters per second squared, like that. And then, so now we have a new acceleration. So we know we're trying to find out when the car stops. So v final equals v initial plus at. So our v final is going to be 0 because we want to know when it stops. Our v initial, which is our v at 2 seconds, is 0.764 meters per second. And then our a is 0.573 meters per second squared. And we need to figure out our t, like that. So move it all over. and then divided by our acceleration equals our t, and our t is going to be 1.333 seconds, like that. And then lastly, for part E, it asks us, will the slope, okay, so if the experiment in parts A and B are repeated with a cart that has the same mass but greater force of friction, so will the slope of the new line be greater, less than, or equal to the slope of the line in part B or I? So we know that the slope is rise over run. So we know it's the rise of A, the increase of A over the run of F, like this, right? Is going to equal to our slope. But we also know that's A over MA, because force is MA. So it cancels out like this. So we know our slope value is 1 over M, like that, right? And then since they say that it's the same mass is always constant, since slope is determined by mass and mass is constant, slope will be the same. When they change the force of friction, all they're going to do is they're just going to shift the graph to the right horizontally, because now we're going to have a new x-intercept, because we know our x-intercept is our force of friction. So if anything, if there's a greater force of friction, our graph is just going to be shifted like this, but there's just going to be the same slope going like that. Thank you.